Spiderivative man talking to you about implicit differentiation. Now, why did all the pictures at the superhero party turn out dark? Because they forgot the Flash!
First thing we're going to talk about is an explicit form of a function. Those are functions where the variable y is explicitly written as a function of x. So here you can see in our examples down here, we have functions where the y is explicitly written as a function of x. Y equals 5x plus 8. Y equals x squared minus 3. Y equals cosine of x. Y equals 1 over x. We have our dependent variable explicitly written as a function of our independent variable. Now, an implicit form of a function, those would be functions where the variable y is not explicitly written as a function of x. Basically, we don't have y by itself on one side of the equation anymore. We have x times y equals 5. We have y squared minus x cubed plus 4 equals negative 3. Y times sine x equals 9x. 8y to the fifth equals x over y. We don't have equations solved for y. We don't have functions where the dependent variable is by itself on one side of the equation. Therefore, each of these functions down here would be in the implicit form of the function. Now, taking the derivative of y with respect to x. So this comes up all the time in implicit differentiation. First thing you're going to do when you're taking the derivative of y to the nth power with respect to x is you are going to use the power rule like you normally would for x to the nth power. So when we're taking the derivative of x to the nth power with respect to x, we just go n times x to the n minus 1 power. So our first step in taking the derivative of y to the nth power with respect to x, bring that n out front, multiply it by y to the n minus 1 power. Take 1 away from your exponent. Then, all you have to do to that same term, you're going to multiply it by dy dx, because technically it requires the chain rule, where you have your outer function is going to be whatever this is to the nth power, and then your inner function is that y itself. So here's how this works. Let me show you. It sounds a little complicated, but it's actually pretty easy. If I'm taking the derivative of y with respect to x, notice that I'm taking the derivative of y. My variable here does not match what I'm taking the derivative with respect to. Because of that, I have to use these two steps. I use the power rule like I normally would. So derivative of y, well, we know it's automatically going to turn to 1, but we could use the power rule if we wanted to. 1 y to the 0 power. Y to the 0 power just turns into 1, so again, it's just 1. Times dy dx. You take whatever you get when you use your power rule and multiply it by dy dx. So the derivative of y with respect to x is dy dx. Let's do another one. Y to the second power. Again, because I'm taking the derivative and I'm taking the derivative of y to the second with respect to x, these two variables are not the same. So what I have to do, follow these two steps. First, I'm going to use the power rule like I normally would. 2y to the 2 minus 1 power, or 2y to the first, times dy dx. There you go. That's how you do that. Next, y cubed. I take the derivative of that with respect to x because we are taking the derivative with respect to x, but this is a y. Those don't match. So what I have to do, follow these two steps. First, do the power rule like I normally would. 3y to the 3 minus 1, or 3y squared, times dy dx. And you're done. Look how easy that is.
I'm part of the Avengers. It's example time.
Now, example 1 says differentiate with respect to x. So this is x cubed. So I'm taking the derivative of x cubed with respect to x. Now notice, these variables match. They're the same. So all I have to do is use the power rule and I'm done. I don't have to tack on a dy dx like I normally would. So this just becomes 3x to the 3 minus 1 power, or 3x squared, and I'm done. Part B, I have y to the fourth power. So again, I take the derivative with respect to x. Notice that because this is a y and this is an x, those are not the same. So I need to use my power rule and then tack on a dy dx. So we go 4y to the 4 minus 1 power, or 4y to the third, times dy dx. And I'm done. Part C, doing the same thing, except this time we have x times y squared. So if we're taking the derivative of this with respect to x, what we're going to need to do is use the product rule, because we actually have two functions being multiplied together, x and y to the second power. So when we're taking the derivative of two things being multiplied together, we use the product rule, which is derivative of the first times the second, plus first times derivative of the second. In this case, derivative of x with respect to x is just going to be 1, like it normally is. Over here, the derivative of y squared with respect to x, these two are not the same variable. Because we're taking the derivative of y with respect to x, we must first use the power rule like we were talking about. You do 2y to the first power, and then you tack on a dy dx, multiply it by dy dx. So that'll be 2y to the first times dy dx. Now we just simplify. What's 1 times y squared? That's y squared. What's x times 2y times dy dx? That's just 2xy dy dx. And you're done.
You try.
Okay, doing the same thing here. We're differentiating with respect to x. So when I take the derivative of this with respect to x, what's going to happen is I have to take the derivative of each term separately. Now, when I take the derivative of this term right here, x and x, those match up. Because of that, we can just use the power rule. So because we have a 3 already out front, we can just use the constant multiple rule, keep that 3 out front until the end. So it's going to be 3, and then parentheses, what is the derivative of x to the 5th? That's going to be 5x to the 4th power. Derivative of 1, derivative of any constant is just going to be 0. So then we multiply these together. 3 times 5 just gives you 15. You get 15x to the 4th, and you're done. Here, we need to take the derivative of each term, just like we did over here. Derivative of the first term, I'm taking the derivative of x with respect to x because these are the same, because they match, these variables match. We are just going to take the derivative like we normally would. What's the derivative of x? That's just 1. So this can become 1. Over here, though, I'm taking the derivative of 5y with respect to x. These do not match. Because of that, what happens over here is I take the derivative of y like I normally would. This 5, again, by the constant multiple rule, just gets to stay out front until the end. What's the derivative of y or x? It's just going to be 1. But then, because I'm taking the derivative of y with respect to x, I have to multiply it by dy dx. So it looks like this. Next, here, I'm taking the derivative again with respect to x. I have y times ln of x. This is a function times a function, therefore we need to use the product rule. The product rule says I take the derivative of the first times the second plus the first times the derivative of the second. Now here, in this first one, we're taking the derivative of y with respect to x. These do not match. So what I have to do is take the derivative of y, which is 1, and then multiply it by dy dx. So it just becomes dy dx times ln of x. Over here, what's the derivative of ln of x with respect to x? Well, those match. So what's the derivative of ln of x? Well, we know that's 1 over x. Now we just simplify. This becomes dy dx times ln of x plus, and then over here, y times 1 over x is just y over x. And you're done. Now let's quickly go over the guidelines for implicit differentiation. The whole point of implicit differentiation is because some equations, it's super hard to solve for y, or it's not even possible to solve for y and get y by itself. So you need a tool to take the derivative when you can't solve for y, when you can't get y by itself. That's where implicit differentiation comes in. So what you're going to be given is an equation that is not explicitly solved for our dependent variable. It doesn't have y by itself on one side of the equation. We have the implicit form of an equation, therefore we need to use implicit differentiation. So the first thing you're going to do is differentiate both sides of the equation with respect to x, like you normally would. Then you're going to move all terms with a dy dx to one side of the equation and move everything else to the other side of the equation. The reason you're going to do that is because in step 3, you're going to factor out that dy dx, and then you will solve for dy dx. The whole goal is to get dy dx by itself on one side of the equation. The reason for that is because that's what you're solving for. You're solving for dy dx, the derivative of y with respect to x, the derivative of your dependent variable with respect to your independent variable. So here, in example 2, we want to find dy dx by implicit differentiation. So we are given the implicit form of an equation right here, and what we have to do is find dy dx, the derivative of y with respect to x. Now, we just follow the guidelines that we just talked about, these steps. Step 1, we want to take the derivative of both sides with respect to x. Now, when we take the derivative over here, we're going to take the derivative of each term separately. The derivative of this first term, because this is a y and we're differentiating with respect to x, what we need to do is use the power rule like we normally would. So this can be 2y to the first power, but then we're going to have to multiply it by dy dx. Here, in this term, when we take the derivative of y with respect to x, these are not the same. Therefore, we again have to take the derivative of this, which is 1, and then tack on a dy dx. So the derivative of y with respect to x, we know now is just dy dx. And then here, derivative of negative x, we take the derivative of x, which is just 1, because these match. You can just leave it as minus 1. And then over here, the derivative of 7 with respect to x, derivative of a constant is just going to be 0. So we have successfully differentiated both sides of this equation with respect to x. Now, step 2 is to get each term with the dy dx by itself on one side of the equation. So here we need to add 1 to the other side. Now we have each term with a dy dx by itself on one side of the equation. We can now move on to step 3, which is to factor out that dy dx from each of these terms. And then step 4 is to solve for dy dx. So to get dy dx all by itself, we got to get rid of this 2y plus 1. So how do we get rid of this? How do we move that to the other side? Well, we just divide both sides of the equation by 2y plus 1. And we end up getting dy dx is equal to 1 over 2y plus 1. So that is how you find dy dx by implicit differentiation. Just follow the steps. Part B, doing the same thing. I want to find dy dx by implicit differentiation. So normally I would just take the derivative of both sides with respect to x first, because that's our first step. But look here, ln of x times y, that derivative would get super messy. So what I want to do first is use my properties of logs, which allow me to, if I use the product property, I can take this ln of x times y and rewrite it as ln of x plus ln of y. That's the product property of logs. Now I can go through my steps of implicit differentiation. The first step would be to take the derivative of both sides with respect to x. So here, when I take the derivative of this side, I got to take the derivative of each term separately. So the derivative of this first term, since I'm taking the derivative of this function with respect to x, and this function has an x in it, I can just take the derivative like I normally would. It's going to be 1 over x. Here, when I take the derivative of ln of y with respect to x, this is not the same derivative as what I'm taking the derivative with respect to. So I take the derivative like I normally would. It's going to be 1 over y, but then I have to multiply that by dy dx. Lastly, I take the derivative of 5x with respect to x. Now these match, so I just take the derivative of x, which is going to be 1, and then multiply it to the 5 by the constant multiple rule. Lastly, this 30, when I take the derivative of that with respect to x, derivative of a constant is just going to be 0. And then I can just simplify this 5 times 1, and I get this. Now I have successfully taken the derivative of both sides of the equation with respect to x. Step 2 is to get anything with a dy dx by itself on one side of the equation and move everything else to the other side. So I can move 5 to the other side of the equation, and I can move this 1 over x to the other side of the equation by subtracting them. Now I have my dy dx by itself on one side of the equation, so I can factor it out. Well, there's only one term here, so I don't need to factor it out. I can just move on to step 4 and solve for dy dx. How do I solve for it? Well, I just multiply both sides of the equation by y, and that'll cancel out this 1 over y here, and over here I get to distribute it to each term, and I get dy dx is equal to negative 5y minus y over x. And I'm done.
You try.
Okay, doing the same thing here. So I want to go through my steps of implicit differentiation. The first step is to take the derivative of both sides of the equation with respect to x. So let's take the derivative of each term over here. We'll start with this term, sine of 2y. When I take the derivative here, this is a y, this is an x. So I'm taking the derivative of y with respect to x. Because these don't match, I have to take the derivative like I normally would, but then multiply that by dy dx. So let's do this. Derivative of sine of 2y. Oh, I have a function within a function. So this actually requires the chain rule. So I'm going to take the derivative of sine, which is cosine, so it's going to be cosine of 2y, times the derivative of 2y, which is 2 times 1, times my dy dx. So it'll be just 2 times dy dx. Here, derivative of cosine of x. Because I'm taking the derivative of cosine of x with respect to x, I just take the derivative like I normally would. Derivative of cosine is just going to be negative sine, so I write negative sine of x. Then over here, derivative of 1 is going to be 0. Again, this required the chain rule right here. I got cosine of 2y times the derivative of 2y, which is going to be 2 times 1, but since it's y and we're taking the derivative with respect to x, we have to tack on that dy dx. Now, let's simplify this. This 2 we can just move to the front, and this we can rewrite as minus sine of x. Now, step 2 in implicit differentiation is to move everything with a dy dx to one side of the equation, and then get everything else to the other side. Well, this term has a dy dx, this one does not. So we're going to add sine of x to both sides. Now we have our term with the dy dx on one side of the equation by itself, and everything else on the other side. So we can move on to step 3, which is to factor out dy dx. Done. You don't really need to factor it out because it's just one term. Step 4 then is to solve for dy dx. So how do I get dy dx by itself on this side of the equation? Well, I'm just going to divide both sides by 2 cosine of 2y. When I do that, I just get dy dx is equal to sine of x over 2 cosine 2y, and I'm done. Over here, I'm doing the same thing. So to implicitly differentiate this equation right here, first step is to take the derivative of both sides of the equation with respect to x. So in order to take the derivative of this side of the equation with respect to x, I got to take the derivative of each term separately. Let's start with y cubed. Since this is y cubed and we're taking the derivative with respect to x, I need to first use the power rule like I normally would. So it's going to be 3y to the second power. But then I have to multiply that by dy dx. Over here, same thing, because it's y to the second power, but I'm taking the derivative with respect to x. I use the power rule like I normally would, so it's going to be 2y to the first power, but then I have to multiply that by dy dx. Same thing here, since it's minus 5y. When I take the derivative of y with respect to x, I have to take the derivative of y, which is just going to be 1, times dy dx. I got to multiply that dy dx on. And then, lastly, we have minus x squared. Since these two variables match, I'm taking the derivative of x squared with respect to x. I could just use the power rule like I normally would, so it's going to be 2x to the first power. Lastly, over here, derivative of constant, we know now is just 0. Sweet, I've taken the derivative of both sides with respect to x. So I can move on to step 2, which is to get each term with the dy dx by itself on one side of the equation, and then move everything else to the other side. So I need to move this minus 2x to the other side, because that's the only term that doesn't have a dy dx. So I'm going to add 2x to both sides of the equation, and now each term with the dy dx is on one side of the equation, everything else is on the other side. So I can move on to step 3, which is to factor out a dy dx. Over here, we just had one term, so we didn't really have to factor out the dy dx. Here we have 3 terms, so I do need to factor out a dy dx from each of those terms. I then move on to step 4, which is to solve for dy dx. So to get dy dx by itself, I just divide both sides by 3y squared plus 2y minus 5, and I have my dy dx, and I'm all done. Now example 3 has 2 parts. The first part says determine the slope of the tangent line to the graph at the given point. The second part says write the equation of the tangent line to the graph at the given point. So first, we just want the slope of this graph at this given point. So to find slope, remember, slope of a graph is just the same as the instantaneous rate of change, the slope of the tangent line, or the derivative at a given point. So how do we take the derivative of this right here? Well, we don't have y explicitly solved for. So this is the implicit form of this equation, which means I can use implicit differentiation. So what are the steps for that? Well, the first step would be to take the derivative of both sides with respect to x. When I take the derivative over here with respect to x, I have a function times a function. So when I take the derivative, I have to use the product rule. So it's going to be the derivative of the first times the second plus the first times the derivative of the second. So I need to take the derivative of each of these, x squared plus 4 and this y over here. So derivative of x squared plus 4. Again, I'm taking the derivative with respect to x of x squared. So I just take the derivative like I normally would. It's going to be 2x to the first, and then I take the derivative of 4, which is just going to be 0. Over here, derivative of y with respect to x. We know now, since this is y and this is x, this is just going to turn into dy dx. And the derivative of 8, we know, just becomes 0. Now, I have successfully completed step 1, so step 2 is to get each term with a dy dx by itself on one side of the equation. Well, here there are technically 2 terms, right? We have this term right here, and then when I have 2x plus 0, that's just 2x. Then I multiply that to y, and I get 2xy. So I have 2 terms. One term here, one term here. Now, to get each term with the dy dx by itself, I just got to get this one by itself. So I'm going to subtract 2xy to the other side. Step 3 in implicit differentiation is to then factor out that dy dx. Well, technically it's already factored out. So we can move on to step 4, which is to solve for dy dx. So to get dy dx by itself, I just have to move this x squared plus 4 to the other side. So I divide both sides by x squared plus 4. And I have found dy dx, which is my derivative of this equation right here. So what did I just find? I found the derivative of this equation right here, which means I can use this to find the slope of this graph at this given point. How do I do that? Well, I'm going to take the coordinates of this point, this x and this y, and plug them in to my derivative here. So I plug in 2 for my x here and here, and I actually am going to plug in y now because I have a y. So now I simplify this. Negative 2 times 2 is negative 4, times 1 is going to be negative 4 still. And then 2 squared is going to be 4, plus 4 is going to be 8. I simplify that and I get negative 1/2. So what did I just find? I found the slope of this graph at this given point. Now, part B wants us to write the equation of the tangent line to the graph at this given point. Well, in order to write the equation of a tangent line at a given point, I just need a point and a slope. Well, I have a point and I have a slope. So all I have to do then is put those into point-slope form. So I plug in my negative 1/2 for my m, that's my slope, and I plug in my point, my x sub 1 and y sub 1 for x sub 1 and y sub 1. Now I could leave my answer like this because point slope form is acceptable, or you can get your equation of your tangent line explicitly solved for y and distribute this negative 1/2 to the x and to the negative 2, and then add 1 to both sides of the equation, and you get y is equal to negative 1/2 x plus 2.
My spidey sense is tingling. Must be time for a U-try.
So we're doing the same thing. We want to first find the slope of the tangent line to this graph at this given point. And again, the slope of the tangent line is the same as the slope of the function. It's the same as the instantaneous rate of change. It's the same as the derivative of this function at this given point. So we want to find the derivative here. Now, you can see we have the implicit form of this function right here. Therefore, we are going to use implicit differentiation. So how do we do that? We have 4 steps. First step is to take the derivative of both sides with respect to x. Now, when we take the derivative over here, we're going to take the derivative of each term separately. Let's first take the derivative of 7x squared. Notice we have x squared, and we're taking the derivative with respect to x. Because of that, it's just going to be like normal. We're going to use the power rule. Here, it's going to be 2x to the first power. And the 7, remember, by the constant multiple rule, just stays out front. So it's going to be 7 times 2x to the first power. Here, this looks complicated, except 6 rad 3 is just our constant. So we can technically move that out front and worry about that at the end. The x times y, though, is still a little complicated because we're taking the derivative of a function times a function. So when I take the derivative, I have to use the product rule. So negative 6 rad 3 is going to be out front. Then we're going to have parentheses, and then it's going to be the product rule. The derivative of x times y plus x times the derivative of y. For this term, we again need to use the constant multiple rule. This 13 we can just leave out front till the end and then multiply it on. But we're taking the derivative of y squared with respect to x. Now, because this is a y and this is an x, what we have to do is use our power rule like we normally would. So it's going to be 2y to the first power, but then multiply that by dy dx. So it's going to be 13 times 2y to the first times dy dx. Then derivative of 16 right here, derivative of constant is just going to be 0. Derivative of 0 also going to be 0. So let's keep going. Here, 7 times 2x is going to be 14x. Here, I need to simplify this in here. So the derivative of x with respect to x is just going to be 1. Derivative of y with respect to x is just going to be dy dx. And then I have this 6 rad 3 multiplied out front. Over here, 13 times 2y times dy dx is just 26y dy dx. I need to now distribute this negative 6 rad 3 to the y, or the 1y, and the x dy dx. Now that I've done that, I can finally move on to step 2 of implicit differentiation, which is to get all the terms with the dy dx to one side of the equation by itself. So here I have 2 terms with the dy dx. These 2 terms, 14x and negative 6y rad 3, they can go to the other side. So I'm going to subtract 14x from both sides, add 6y rad 3 to both sides, and I get this. Now, each of these terms has a dy dx, so I can move on to step 3, which is to factor out a dy dx. Step 4 then is to solve for dy dx, so I'm going to divide both sides by negative 6x rad 3 plus 26y, and I get something that looks like this. Now this looks crazy, but what I'm trying to find is the slope of this graph at this point. I found the derivative of this graph at this point. This is not the slope. To get the slope at a particular point, I plug in the x and the y coordinates for the x and the y in this derivative equation. So I take rad 3, plug it in for x here and here. I take 1, plug it in for y here and here. And now all I have to do is simplify. And when I simplify this, believe it or not, it simplifies to negative rad 3. So I have found the slope of this graph at this particular point. All that's left is to write the equation of the tangent line to the graph at this given point. So to write the equation of a tangent line, I just need a point and a slope. Well, I already have a point, and I just found my slope. So I take the slope and the point and plug them into point-slope form. I take negative rad 3, plug it in for my m. I take rad 3 here, plug it for my x sub 1, and take 1, plug it in for my y sub 1. I can then leave it like this in point-slope form. That is the equation of the tangent line. Or you could put it into slope-intercept form, which involves distributing this negative rad 3 here and here, and then adding 1 to both sides. Now, example 4, we have 4 parts here. It says, first, we're going to find 2 explicit functions by solving the equation for y in terms of x. Then part B, we're going to sketch the graph of the equation and label the parts given by the corresponding explicit functions. Then we're going to differentiate the explicit functions. And then lastly, we're going to find dy dx implicitly to show that the result is equivalent to the part C. Okay, so let's start with part A. We're going to first find the two explicit functions by solving the equation for y in terms of x. And that makes sense, right? Because explicit functions means you're solving for y by itself on one side of the equation. So we just need to solve for y. So let's subtract x squared from both sides, and we're going to square root both sides. Now, when you square root a variable squared, on the other side, you need to put plus or minus. So our two explicit functions are going to be y is equal to the square root of 4 minus x squared, and y equals negative square root of 4 minus x squared. And now notice that x has to be between negative 2 and 2, because if x is any bigger than 2 or less than negative 2, this becomes negative inside the radical, and we can't have that. We can now move on to part B, which involves sketching the graph of each part of this function. So how do we do that? Well, we know that this right here is a semicircle with a radius of 2. This also is a semicircle with a radius of 2. It's just this first one being reflected over the x-axis. So it looks something like this, where this top part is going to be y is equal to the square root of 4 minus x squared, and the bottom part is y equals the negative square root of 4 minus x squared. Cool. So we can move on to part C now, which involves differentiating this explicit function right here. So how do we differentiate this? Well, we're just taking the derivative like we normally would. If we take the derivative, we don't want a square root, so we change that to a rational exponent. That's just going to be a 1/2 exponent. So when I take the derivative now, what I'm going to do is, you can see I have a function within a function. So I need to use the chain rule. And the chain rule says I take the derivative of my outer function first. So I use this power and use the power rule. It's going to be 1/2 4 minus x squared to the negative 1/2 power, because I subtract 1 from this. And then I multiply that by the derivative of my inner function. And the derivative of my inner function is going to be 0 minus 2x to the first. Then I can simplify that and just make that negative 2x. Multiply that out front to the 1/2, and it just becomes negative x. Now, since I have 4 minus x squared to the negative 1/2 power, I'm going to take that and move it back to the denominator, where it becomes positive 1/2 power. And since it's a 1/2 power, I can rewrite that as the square root of 4 minus x squared. Now, this plus or minus, anytime you have a sign out front, I can put it with my numerator or denominator. My numerator already has a negative, so I'm going to put it with my denominator. And look at this. Don't I know something that equals plus or minus the square root of 4 minus x squared? Yeah, right at the beginning of my equation, I knew that y equaled that. So if I wanted to write this a little nicer, I could just take y and substitute it in for plus or minus the square root of 4 minus x squared. And I have found my derivative of my original explicit functions. Now, part D, I'm going to take the original equation and implicitly differentiate that to show that I can get the same thing, and it's much easier. So this is why implicit differentiation is useful. I'm going to use the steps for implicit differentiation to show that I get the exact same thing. So, implicit differentiation. First step, take the derivative of both sides with respect to x. Here, I'm going to take the derivative of each term. Derivative of x squared, again, these match, so it's just going to be 2x to the first power. Over here, derivative of y squared. These do not match. I'm taking the derivative of y squared with respect to x. So I'm going to do the power rule like I normally do, 2y to the first power. But then I'm going to have to multiply it by dy dx. And the derivative of 4, derivative constant, is just going to be 0. I then am going to get everything with a dy dx by itself on one side of the equation. Everything else has to go to the other. So this 2x needs to go over here. So I subtract both sides by 2x. I then factor out a dy dx. Well, I don't have to because it's just one term. Then I solve for dy dx by dividing both sides by 2y. I then can simplify this. The 2's cancel each other out, and I get dy dx is equal to negative x over y. Wow, that was much easier than using the chain rule and simplifying like this and then substituting.